algorithm, I guess, right? Given any pair of orthogonal Latin squares, you may freely just like permute the numbers. Like if I replace all these 2's with 3's, it would still be a Latin square, and it would also still be orthogonal because no ordered pair is repeating because I'm just moving them. That justifies the arbitrariness of my decision given any one particular line to sign it any one particular collection of numbers. Remember how I pointed to this line and said, let's just call this 1, 1, 1? There was nothing particular about that. Similarly, via kind of a similar argument, one can force any pair of Latin squares to be in the standard configuration, which these two are. And you can sort of argue that it would be impossible for there to be like another one. Anyway, yes?
This is not related to that, but does that mean that if you had a order 4, it would produce 5, because n plus 1?
It would produce 5 squares. 2 of them would be these that are Latin squares. Yep. And so yeah, the problem you're going to do for homework is going to produce, given a finite projective plane of order 4, which really means 5 points per line, that you'll get 3 mutually orthogonal 4x4 Latin squares out of that. And then it works for 5, and then it just straight up doesn't work for 6. Because complicated, well, no, not that complicated reasons if you know what you're talking about, but I only have to. You just, in a 6x6 Latin square, you cannot find even 2 mutually orthogonal Latin squares of order 6. We already talked about this, right? This is the Euler's 36th officer's problem. And so there are no finite projective planes of order 6, and that's because there are no finite fields. Because it's also true that there are no finite fields of order 6. 6 is the first number which is not a power, is not a prime or a power of a prime. Anyone have anything to add? This was not a very efficient class, but we did get it. It was all accomplished. Woo! Yo! Oh, we're gonna have a test like really soon. Like when should it be? Like Friday.
What?
Woo! Good. Here's what's on it. Everything from chapter 8. Plus, I might teach one little quick thing on Wednesday. Occupancy problems.
Okay.
What's an occupancy problem?
Latin squares.
Occupancy problem?
What's an
And
occupancy problem?
The ones with answers like
Stirling numbers of the second kind, partition numbers, section 8.1.
It's like you're trying to get things out of the file.
Woo!
I don't even
Good. Goodbye, video. Do you have anything you want to say on this?
Oh yeah.
Wait, Stav is going to say a couple things really quick, and then the bell's going to ring.
Well, let's comment on this. Like the reason we did this first step of picking a line at infinity and picking points at infinity is pretty much to make this diagram look like this one. Now we can make a vertical one. Like we can start taking points at infinity and like going backwards to derive Latin squares from them. And also this gives you the horizontal Latin square and the vertical Latin square. That's like why we arrange the grid in points like that, and then we get everything else. Yeah.
If you like had a finite projective plane of like any order, could you get like all of the possible orthogonal Latin squares from that?
Yes,
Yes.
but there isn't.
Only if they're isometric, right?
Isomorphic. La, 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 la. I can't imagine this algorithm not working. It just doesn't. Oh, it's not just always true. Yeah.
The algorithm guarantees that you get